Oh, by the way, we take a break after 50 minutes for 10 minutes. I think that's the usual. Y'all do that in other classes?
This is my first in-person.
Really?
Me too.
So at 1:20, we're going to take 10 minutes.
I was worried about that.
I find that every time I start one of these courses in statistics, I'm never consistent. I do it a little different every time because I never really know what's the correct thing to start talking about. But no doubt that in week 1, it is a bunch of definitions of words, and that's the majority of it. And then right at the tail end, there's we finally start doing, I guess, something that would qualify as math, but not really. So prepare for a bunch of vocabulary. I mean, there must be 20 or more words. And it's not like you could take a guess as what they mean. Most of them you would have no idea. Unless you had the class before or something. So let's start with this concept. So this is probably obvious. Data, whatever data is, consists in or of points. So a collection of these points we would call a set. So then if I survey a bunch of people and if I asked all y'all what your height was, then each one of those numbers is a point. And then the collection of it would be a data set. So if I'm talking about a set, a data set, or if I'm talking about a point, the point would be a member of the data set, and it would be some kind of measurement. Or an attribute. The points do not necessarily need to have any kind of numerical content. It can be like all y'all's hair color, okay, which is not a number. A variable is a little different than what it was like in algebra, where it was this x, right, or something unknown and you had to solve for it. In statistics, a variable is like a concept. It's the feature that you're going to be measuring or describing the attribute of. So for example, I could say, here, let me declare a variable, the hair color of my students. So this is some feature, and and that hair color has lots of different options, so it can vary in its value, and that's why such a thing would be a variable. Or maybe we say housing prices in DFW, another variable. Okay, so implicit in these definitions of the variables is the place where I'm going to get that information. I didn't say the hair color of New Yorkers, right? It's my students. So here inside the definition of the variable, you can find what's called the population. The population is always big, and it's described in the variable. It's declared by the variable definition. It upsets me when we get to the signature assignment, the last thing of the course, and students remain confused about the difference between the population and the very much smaller subgroup of the population, or subset of the population, which would consist in just the measurements that they took and formed their data set. Right? So if I'm wanting to know about housing prices in DFW, you would agree there's a lot of houses in DFW. It would probably be a huge, difficult task to find out what's the price or value of every house. I don't want to do that. There's way too many. That's a big population. So instead, statistics is all about collecting a sample of that population and seeing what we can learn about the population just by looking at the sample. The sample is a much smaller subset of the population. It's like if the population was all the stars in the visible universe, observable universe. That'd be an awful lot, trillions and trillions. And then I want to get a sample of those stars by just going and randomly picking one from each galaxy. And there's billions upon billions of galaxies. So even though I'm getting one star out of a galaxy, each galaxy has, 200 million stars or more. My sample would be much smaller than the population, but still massive. Okay. So the sample is a much smaller subset of the population, and when you collect that sample, it would form a data set. So the sample is a data set. It consists in points. Each of those points is a member of the population. And there's some attribute about those points that we're trying to describe, either with a measurement or a description. Now, that's all the beginning intro stuff. Now, variables have two distinct classifications. Variables can be discrete, not that kind of discrete, right? They're not like on the down low. They are discrete. Or they are continuous. You could spend a long time discussing the difference, and we're about to. Not that long, but it's understanding the difference between these two. It's possible that it can be tricky, or you might get it right away. You know, who knows? Now, so that you can understand the difference between discrete and continuous, let's talk about some non-statistical examples just for a minute. Let me give you the definition of countable. We would say that a set, like a data set or a sample or a population, a set is countable if we can assign each member of that set with a unique positive integer. The positive integers are 1, 2, 3, 4, and so on. Based on this definition of what it means to be countable, if I have a finite collection, is it countable? Of course. I can just look at it and go 1, 2, 3, 4, 5. I get to the end, and that's it. That's all of them. Every member of that set got assigned a unique positive integer. So finite sets are countable. What if my set is grains of sand on planet Earth? I'm not asking if someone will.
You could.
That wasn't part of the definition, right?
Right. So it is finite.
Right.
Because
It is finite.
It can't change. It is.
It is finite.
Okay.
If it grew to infinity, then the sand would fill up the universe.
Right.
So there's a finite number of grains of sand on the planet. That's a countable collection. I'm not going to do it. It would take generations of people to get that done. But it's possible. So even if your collection is very, very large, if it is finite, it is countable. So even if I extended it to be the number of stars in the observable universe, that's finite. There's not an infinite number of stars. If there were an infinite number of stars in our observable universe, we'd be inside one right now, because it would fill up the whole space. What about the collection You see my scheme? Okay. Is this a finite collection? What's the last element then? What's the last one?
CZ.
Then what about DA?
No, so DA it would go all the way through ZZ, wouldn't it?
No. So you said ZZ.
Yeah.
So then, after ZZ, you would have A,
Okay.
and then A, B.
Then it's not finite.
It's not finite. I could do this forever. Each one of these members would have a finite length, but they would just keep growing and growing in length forever. And then this whole collection has an infinite number of members. Like, call these names, or words is what you would call them. That's a word, infinite number of words. Each word has a finite length. Is this collection of words countable? Because at some point, it literally would have every word that you could ever write in this collection, right? I mean, it doesn't look like it now, but, the word boy would be in here somewhere, eventually. And so would West Let's look back at that definition of countable. If I can assign each member, so assign each word with a unique positive integer. Then I could go 1, 2, 3, that's 26, 27. I just keep counting. Am I ever going to run out of numbers? No. So then, isn't it true that each one of those got assigned a unique positive integer? Yeah. This is a countable collection. Some infinite sets are countable. What do you think I'm going to have to talk about after this? If finite sets are countable and then some infinite sets are countable, what's the third logical thing that you would think? There's got to be some sets that are not countable or uncountable. Naturally, they would have to be infinite, right? Because if every finite set is countable, but only some of the infinite ones are countable,
Which infinite ones are not?
then there's got to be some other infinite ones out there that are not countable. Okay. Well, if you're a good guesser, then you would know the answer to this one. This notation is interval notation, right? It's a segment of the number line. So it consists of all of the decimal numbers less than 1. Between 0 and 1, not less than 1. All the positive decimal numbers less than 1. So it would consist in numbers that look like 0.012345, so on. That'd be one of them. It's an example. Or maybe you have 0.98722222 forever. Or you could have 0.1010101. It just does that forever. Or maybe there's, I need one more here, or maybe there's 238, 239, 23, something else. Pi is on there. Pi is not on there. Pi minus 3 is on there. Those last 2 digits I'm not sure of. Just made them up. So all of these numbers live in here, right? And it does not have to be the case that all of the numbers in there are irrational, right? You could just have this one, right? 10%, 0.1, where it's just zeros forever after that. That's a rational number. But there's going to be a whole bunch of them that are like pi minus 3, where there's no, it just goes on forever. It doesn't come to some point where it's all zeros afterwards. It doesn't come to some spot where it just repeats over and over. right? This one would be a rational number because it's repeating. You could transform this into a fraction, but this one could not be written as a fraction. The definition of countability said that it would be countable if you could assign every one of them an integer. And it's pretty easy to just go through and go 1, 2, 3, 4, 5, right? And assign it that way. So that way you know they're all unique. Okay. Suppose for a moment, just suppose that I had made here a list, that this list would just go on forever. Suppose here that I have a list that just goes on forever, and my claim would be that on this list, I have put every one of those numbers in this list, or in this interval. You understand what I'm saying? So here's an infinite list, and I'm saying, suppose that I have written down all of the possible decimal numbers that are positive and less than 1. And you come along and say that you can construct a number that's not on this list. You do it in the following way. You go to the first number on the list, and whatever digit that is, just add 1. Right? If you happen to come to a digit that's a 9, just let it roll over to 0. So, to get the second digit of your number, I'm going to look at that 8 and make it be a 9. Just 1 more. And then that's a 0, so I'll have a 1, and that's a 2, so this is a 3, and that's a 9, so this would roll back over to 0. And I just keep doing that all the way down your list forever, because your list is infinite. Then this number does not have any of these integers assigned to it, because it cannot be the first one. It's different at this position, and it cannot be the second one. It's different at that position. Likewise, it can't be equal to the third one because it differs at the third position. And it's just going to be different from every number on this list with this construction method. But you exhausted all of the integers right here. All the integers got used up. So there's no more integers available to assign to this one. You understand? If this number was on my list, then there would have to be one of these numbered ones where it agreed on every position. But it cannot agree on every position, because by construction, the manner in which we constructed this number, there will be at least one digit where it does not agree. Say I went down to the 1,000th row. Then on the 1,000th digit, they would be different numbers. It could be the same everywhere else. But at that 1,000th digit, they'll be different. And that one will be 1 unit bigger than whatever this one was.
Why can't it just be 1,001? Like, or is it because we're talking about like this specific set of numbers?
No. So my listing here has to go on forever, right? Because naturally I'm saying, look at me, I've made a list of all of the decimal numbers that are between 0 and 1. So I have an infinite collection here, and I've attempted to assign each one of them an integer. I've said that this is the first one on my list, and this is the second one on my list, and so on. And I have an infinitely long list, right? Then no matter which row you select, you can select any row. Select the 1,000,000th row. Come out here 1,000,000 digits into this decimal number. Then the one in the 1,000,000th row would be different from this one up here, the yellow one. Where would you know for sure it differs? At the 1,000,000th digit. So it doesn't matter which row you select, the number in yellow will be different than the number on that row.
Is it because the ones you have up there aren't following a pattern, as opposed to when you put the letters, there was following a pattern, so we knew it would keep going in that same way?
Mm-mm.
Okay, because if you did it
It doesn't matter if there's a
a
pattern or
similar
not.
way, wouldn't you be able to, like, if I started with 0.1,
Mhm.
0.10, and then I went back and did 0.01,
Well-
0.0, and then I did that, and I did that, wouldn't you eventually, following that same pattern over and over and over again, it's the same, to me, that's the same infinite that the letter example was.
So let's try and follow that logic. So if I could have some sort of technique to systematically count all those numbers, then you're envisioning something like 0.100, and it's just zeros forever, right? After that. Because even a number like 0.1, this number here is equal to 0.1. It is implicit in the definition of 0.1 that all of the other numbers after it are 0.
But if I did that, so then I did 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then repeated that. And then the next time I did 0, 1, or 0.1, 3, 4, 5, 6, 7, 8, 9. And then 1, 4, 4, 5, 6, and I follow a pattern where I'm repeating it, and then I change it each time the exact same way. Wouldn't it, if we're going on for infinity in the same,
You're saying eventually you're gonna stop.
no, I'm saying like, then, I don't wanna say this word, because it's this class, but I feel like, if it's truly going on for infinity,
Mm-hmm.
and you do it in a patterned way, like you did with the letters, eventually you would have created a pattern that accidentally stumbled on the number that you created.
I understand what you're saying. Does this scheme fit your idea?
Yeah.
Okay. So it goes 1, 2, 3, 4, 5, 6. This list right here would stop at 0.90000, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the next one, we would start back over at, we'd start back over at 0 here. Is this what you had in mind?
Yeah.
Okay. Tell me
So-
what the next one would be right here.
So then, I wouldn't have started with 0, but if you're gonna start with 0.
It can literally be whatever you want. It doesn't matter if
I
we
would
go.
have done like 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9. I followed it all the way through. And then the next one I would have done 1, 3, 4, 5, 6, 7, 8, 9. 1,
Hold on,
3,
hold on, hold on,
4.
hold on,
You
hold
know
on.
what I'm saying?
So
I wouldn't have started there.
you wouldn't have started here?
I mean, I would have, because that is 1. That would be
You
9.
want 0.1 and then 0.12
Yeah.
and then 0.123.
and then-
Okay.
Yeah, and so that would be 9 of them. I would count and you would have 9. And then on the 1,000th iteration of this, I would be at a point where the fifth place would actually be a number that I'm repeating again.
Well, I mean, if it's repeating again, then it's on your list twice. You just throw it out, you don't need it.
Well, I mean, if they're.
The objective is to count all of the possible numbers like this.
Mhm.
So, if you could come up with a scheme, there actually isn't one is the thing. That's why it's hard. Because there's not a first one. There's not a least one. There's no place to start.
And so that's why this is different than your letter example, because you started with 1A.
Yeah.
Okay,
It's called well-ordered. This is not.
okay.
Because there's not a least element. So, what could the next one be? It would be 0.1234, 0, 0, 0, 0. And then once you got to 1, 2, 3, 4, 5, 6, 7, 8, 9, how would you start the next cycle?
If I was doing it in a organized way, I would have, for that set, I would repeat the 1, 2, 3, 4, 5, 6, 7, 8, 9.
Mhm.
1, 2, 3, 4, 5, 6, 7, 8, 9. And then for the next one, I would,
Well, then you would have missed some of the numbers, is the thing.
well,
Because then a number like pi minus 3 wouldn't be on there. Because they would all start this same way. 1, 2, 3,
Well,
4, 5, 6, 7, 8, 9.
no, well, yes, but then that would be one of my sets. And then I would do one that starts with 2 and do it all the way through that way. And then one that starts with 3 and do it all the way that way. And have the different repeating and the different,
Okay.
In order for something to be countable, it has to have like a minimum. Is that like a starting point? Is that kind of like? And that's why this, the last sentence.
That's a highbrow question, and I think the answer is yes. Because if a set has a minimum element, no, that's actually not true. I'm sorry.
Okay.
Because look at this. The interval from 0 to
Yeah.
1, it will turn out is uncountable. And let me just union it up together with the number 0. Then it has a minimum element now. But there's not an immediate successor to 0. You know what I mean? Okay.
You said well ordered.
Yeah, well-ordered is what it's called. Okay, so there really is no good numbering scheme because of that. It doesn't matter what you do. Suppose that you did like my numbering scheme for, it convinced you that I had captured all of the possibilities. I mean, the best way to visualize that I've captured all the possibilities is to just, shotgun patterns. Just have a random pattern of them and make the assertion that on the list, my claim to you is that I have listed every one of them. And I haven't missed any of them at all. That's my claim. And that what I did was I went through this random, it's just randomly put here, and I labeled each one of them 1, 2, 3, 4, 5. It kind of establishes now that my list here has a least element, or it's assigned this, and then that one is the least of all these. So then it kind of creates an ordering over here that's not less than or greater than. It's an extension of what its name was. The name of this number is 1, and the name of this number is 2, and the name of this number is 3. And it goes on forever to infinity. But then there is a number not on this list. No matter what list you make, no matter what scheme you have, you can, in an instant, construct a number not on the list. It's called the diagonalization argument. Starting at the first digit, make this one be different. And then on the next row, the second digit, this one is different. And then on the third row, this one is different. And even if down here at some random spot at 1,286,452, on that row, we got down there and suddenly the number started off like 0.19130, and then it has a 2 here, or something, or whatever you want. It could just be zeros forever after that. My number up here will still be different than this one, because it agrees, it would agree for how many digits? 1,286,452 digits. They would be the same. So this one would just have a bunch of zeros for a really long time. And then when we got out here to the very last zero on this one, and then after this many digits, it suddenly changes to ones. Yeah.
Does this only apply because you have the zero, or can it be like any?
No,
Okay.
it doesn't matter what number.
Okay.
It doesn't matter what number, because the one up here will differ by that one by 1 unit. So that 0 and that 0, they're at the same spot. Those are at the same position of number of digits after the decimal. 1,286,452 digits after the decimal. We're right here, we're right here. These two agree with each other. Now, the next digit on this one was a 1. That one's going to be a 2. Now they're different. Yeah.
Okay, so I understand what you're saying now, and then we said about the union of zero. So let's just say, like, the zero between the 0 and 1 is not countable, and then you said it doesn't matter which number it is, it's still not countable because the numbers still wouldn't come out the same. But you said if we had a union of 0, then it would be countable because
No.
No?
It wouldn't be
Okay.
countable. It would just have a least element.
So it has nothing to do with because there's a least element.
If a set has a least element,
Uh-huh.
it can still be uncountable.
Okay,
Yeah.
gotcha.
Because this argument shows that the decimal numbers between 0 and 1, you cannot count them all, because you will run out of integers.
Get what you're saying, okay.
Even if I went on to infinity here, I don't have any more integers to give to this one. I have built for you a number that's not on this list. And no matter what list you make, you can just do this diagonalization argument. Just go through and add 1 to each digit. And you'll build a number not on the list.
So any example, if they're saying, okay, how, is the, like, between 2 and 3 countable, it's always gonna be no, because you're never gonna get
Right.
the same, okay, simple.
Every segment of the real number line is uncountable. So here's my real number line. There's 0, there's 1, and right here in between 0 and 1, there are more numbers than there are integers. Now, back to that word continuous. Don't you have an intuition that this real number line is continuous? Whatever continuous might mean. It's completely filled in, right? in between 0 and 1, there's every possibility you could imagine for a decimal number. Whatever somebody wants to write down, yeah, it's in there. 0 point, blah, 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 whatever you say. Whatever you say, it's in there. And so naturally, the whole number line itself is uncountable, but then, of course, any little piece of it is also uncountable. But just those points, 0, 1, 2, 3, that collection is not countable. So then you can rephrase discrete and countable, or excuse me, you can rephrase discrete and continuous in the following way. Variables that are discrete are countable. Even if they are an infinite collection, if you can count them with our technique, it will be discrete. Whereas continuous variables are uncountable. And that is the key to understanding the difference between discrete and continuous. Let us take our 10-minute break, and when we come back, I want to open the homework and answer the questions they ask in the beginning about discrete versus continuous. That diagonalization argument was made famous by a German mathematician named George Cantor. Don't worry if it feels strange, because even the world famous mathematicians at the time thought it was gibberish. But very soon afterwards, it became regarded as some of the best realizations that had ever been made.
this your first class or your first class in person?
First class in person.
What else? have
I'm in Foundations of Higher Education.
you- Oh, okay.
Yeah.
How many prereqs do you have to take?
I have this one, and then chem and, cultural pluralism, and then English 2, and one other one. So,
A random array.
Yeah,
So you had
exactly.
a lot of sciences already?
yes, yeah.
I had no sciences, so
Okay.
I did anatomy, physiology, just finished chemistry, and now I'm in microbiology, and I take pathophysiology,
I have to take patho too.
and then I start clinical, like nursing core
In
in
the fall.
June.
Okay.
Yeah.
Okay, that's awesome.
Yeah,
That's
well,
awesome.
I mean, I started
How's chem?
in April. Online, it was pretty easy.
Okay. Okay,
I did not do it in person.
okay.
I don't know if that's gonna bite me when I,
Right.
in class, but,
Okay. That's good.
what's your name?
Canerica.
Kanerica?
Mm-hmm.
Nice to meet you.
What's your name?
June.
What's your name?
I'm Shannon.
Shan.
How far along are you in?
So I started like from scratch, like with no training or anything. So next I take patho, and then after that I'm in course. I start core in June.
Oh, cool.
You do too? Yeah.
I'm taking Paco next term.
Mm-hmm.
Yeah.
Yeah. When do you start?
In fall.
In fall.
Yeah.
Have you done all of them in person or have you done online and in person?
Online and in person.
Okay.
Mm-hmm. So, at first, like when I first started, I did in person, and then I did online, and now I'm back in person.
Okay.
Yeah.
Are you gonna do Paco in person or are you taking
I
online?
want to do that in person
Okay.
because it just depended on the class that I had. Like if I felt like I needed to, like, I don't know. It's just how I learned. Like if I think the class is going to be more difficult, then I'll do it in person and not
Yeah.
online. Yeah.
I would say right.
Mm-hmm. I feel like I can handle it. So okay. Like the writing classes, I was like, I can do that at home.
Yeah.
I really need to be up here.
Yeah.
But yeah, if it's harder, then I'll do it here. Yeah. Or if I think it's gonna be harder.
Have you guys taken stats before?
In high school, but that's it.
Yeah,
Mhm.
I haven't either.
My first degree is in radio, TV, film, so I take like college algebra.
Yeah, yeah.
And I thought I was tracking until we got to that number thing and I was like,
Yeah, yeah.
You said you already have a degree? Do you?
No.
No? Okay, me neither. My, when I was in class last time, everybody was like, oh yeah, I'm already in this, and that. And I was like, oh, I haven't done anything. Yeah.
this is my third career.
Oh, okay.
I haven't decided what I want to do.
Which one is it?
but,
Yeah.
I do kind of like the structure though.
Hmm.
You may have missed it.
What?
He said he'll do his lecture and then we'll do the homework together. And the homework will be done before you leave.
Yeah,
And then he
I
said to
love
do the
that.
quiz right up, like, because
Right
you're not
after.
done super late.
Yeah, I had him for the regular college algebra because I have to take it as well.
Mm.
And that's what we did. So like we'll do the homework, but his sometimes are different questions, but the type of questions is in the same order.
Mm.
So I used to do it like while he was doing it, but I would put in my numbers and then the steps, then I would just do it with my numbers, and I would be done. And then like right after class, I would do the quiz, and it would take me like 10 minutes. or so,
Okay.
and
And you do
have it out of the way.
In his class too?
Mm-hmm.
Okay.
Yeah. So I wouldn't have to do it when I get home unless I need to like touch up on anything.
Mhm. Tell me that again. You did your numbers? Like you would look
Yeah,
at the quiz
so-
and what your quiz numbers were?
No, not the quiz,
Okay.
for the homework. So he would pull
Oh,
up the
I
homework.
got you. And
Yeah.
you would pull up your homework
And I'll
and
pull
your
up my
questions
homework.
would be different. 'Cause
Yeah.
our questions are different. a little different.
Mm-hmm.
Got
The same, like if it's like
So
one
it's the
type
same
of,
concept.
it's the
but-
same concept, but different numbers,
Mhm.
or in this case,
Got
I
it.
think definitions. I don't really know what the homework's gonna be.
Right, right.
Yeah, yeah.
Yeah.
Okay, that's cool.
But if it was numbers, then he would have like his numbers, and then we'd have our numbers. But it's the same type of question.
Got it.
So so I would just plug mine in.
And then you said the quiz is kind of in the same order for that type of question?
Yes, so the quiz is kind of exactly like the homework. So we wouldn't do the quiz in class though, we would do it like on our own time, but I would just go into one of the study rooms and then do the quiz.
That's what he
myself.
said to me.
Yeah.
Yeah, or recommended.
Yeah.
So then all you gotta do on your own is the discussion, like at home?
Yeah, that's it. It's only discussion, homework, and quiz, that's like it.
That's, okay.
That's
That's
incredible.
awesome.
I'm super excited about it.
Yeah.
That's awesome.
Mm-hmm.
All right.
Cool.
Yeah, I think I passed his algebra class like with an A,
Oh,
like a 98 or something.
oh wow. That's awesome.
Yeah. When he was explaining the whole number thing, I was like, okay, I don't understand it.
Yeah.
But last time I had him, he explained everything like perfectly, but I guess it's just that little thing. It's just like,
Yeah. Yeah, that was weird.
yeah, but I don't know what homework is. I hope it's definitions. Easy 100.
I looked and it's only 15 questions, so I just didn't open them.
I forgot to mention. So I said, take the quizzes as soon as you can after class because we're going to try and get all the homework done in each class. But then you have some weeks where you don't have quizzes, you have a midterm instead. The quizzes and the midterms you take, on your own time outside of here. And then when we get to the end of the course in week 9, during our week 9 meeting, we'll take the what is it named? The final exam in here together. Okay? And you will prefer it that way. Because I look over your shoulder and make sure everything's going right. And then there's the signature assignment, for which there will be a corresponding video that goes through step by step and shows you how to do it. And in that week 9 meeting, we will have enough time to do the whole signature assignment. So it'll be really easy. Homework 1. Let me say before we get started here that a good majority of the questions have the wrong answer by the publisher. And the reason for that is because the publisher usually has not stated the variable correctly to yield the answer that they want. I write them letters all the time and get stuff changed. Sometimes they don't agree with me. That's okay, they can be mistaken. Sometimes they change it. But I know what they intended to say every time. And the majority of the problems are either the statement of their variable, the statement of their population, or the fact that no one has witnessed an infinite collection of anything ever. There isn't one that we know of. Because we can only see so far away. You can only see, if you look out with your telescope, you can only see back 13.8 billion years. And the speed of light is finite, so we live inside of an observable universe. We really don't know if the universe is infinite and just goes on forever, or not. There's no way to know. And there might be a way to know, but no one right now knows how to do that experiment. And until you think about it critically, things like the number of grains of sand on Earth, if I just went up to anybody on the street and asked them, they'd think it was, they'd naturally conclude, given that the number is so large, it must be infinite, but that's different. The number of grains of sand on Earth is closer to 0 than it is to infinity, because there's that much more numbers after it. So here we have the heights in inches of female students at a college. They don't mean at a specific college. Because if it was at a specific college, then there would be a finite number of female students at that college, and I could just make a list of all their heights, and it would be countable. But that's not what they mean. They mean here that it's at any college, including the colleges that have never been built yet, and all of the female students that had ever existed in the past and that will ever exist into the future. And not just the female students that will exist, but any conceivable female student, whether or not they ever existed. That's a much larger population.
Closer to 0 than it is infinity.
How come you think it's still countable? So I'll give you one reason why I would think that that could be still countable, and it may not be based on one of the things I said. So, how many cells do you have in your body? Is it finite?
Yes.
It's finite. Okay. Then let me just make a different, another student that's just like you, but with one more cell on the top. Then think about all of the different sizes of that a cell could be, right? It won't shrink down to 0, right? So there will be a little gap between your height and the next one's height. If you did that, and it had that gap, it would be countable. Because then that would mean that all of the different heights that you could ever create would just be individual points on the number line. In order for it to be an uncountable collection, I'd have to do something like adjust that one cell. I have to change the angle that it appears on your head, so that way I could construct this whole collection of females based on your height, where you are the first one, and then I build the next one. I put the cell right on top, and it changes your height. But then I start to scoot it over on the top of your head, so that way when I measure the height, it smoothly change. So you're standing up against the wall, and I bring the next one over, and the pen has to smoothly change between all of the different possible heights as that cell goes over to the side of your head. And then finally, I'm just touching the top of your head now, and then that person would be the same height as you, so that's not a different height. They are talking here about a continuous variable. Their claim is that heights of female students at a college is continuous. Well, you have to qualify that a little bit better for it to be continuous, because things like heights, if I just look at a ruler, then it is just like a number line. It's a mapping from this physical object to the number line. Right? So you could have things that are this length, and you could have things that are this length, and you could have things that are any length in between those two. Well, that's an interval. That's an interval of lengths. So it would be uncountable. But the nature of the variable that they have declared is not worded properly to correctly express that. If it's just female students at some college, it would be countable. But if I then throw in any college ever into the past, into the future, any female student ever into the past, into the future, even the ones that never existed, then you could have an uncountable collection of heights. Yeah.
So we need to put in our head for these questions, since you said they're most likely worded incorrectly.
Quite a few of them
They
are.
don't specifically state, like, let's just say if we were talking about like states, like if they don't specifically, or a city, let's just say if they don't specifically say like Garland,
Mhm.
which is like smaller than like the whole Dallas Metroplex. Let's just say if they specifically said Garland, then it would be countable, but since they are saying any state, then it would be uncountable. Are you saying unless they specifically like say, I think?
Because we live on Earth, inside the universe, we will not ever encounter an uncountable collection of anything. Even if I say the number of humans that have ever existed and will ever exist is a finite collection. The number of people that could ever live in Garland is finite. And even if I extended it to the earth, it's finite. We would have to also throw in all of the humans that never did exist, because then I can just start defining them arbitrarily. I could look at my list of all the humans that ever existed and say, okay, which heights do I not have? Then let me come over here and say, well, all the heights that I don't have, I'll define over here in this list of people that never existed, all the people who have the heights that aren't on this list. And then merge them together, and it gets filled in, just like the number line. There's no gaps, no breaks. I would have a list of possible humans, and on that list would be every possible height, just as precise as you want to measure it, to the infinite decimal place.
Okay, another question. You just said that this question right here
Uh-huh.
would be continuous.
When I put continuous, it will count it correct.
But you just said.
The fact is, though, is that this, the way it's written,
Right.
is not continuous. It's finite.
Okay, yeah, that's why that confused
Okay.
me, because the example that you just said is kind of just like this. You would say it doesn't matter if they came before or after, if they will, then it will be
Mhm.
finite. But you just said this is continuous, but it's the same thing, but you're saying that it won't.
Okay, hold on.
Okay,
See the way that this is worded,
yes,
finite,
okay.
because they're talking about a college,
A specific.
like this one.
Okay,
How many females go here? Is that finite?
yeah,
Yeah. How many females ever went here into the past and into the future? Even if I gave them that, which they didn't state, it would still be finite.
okay.
I would need to also consider all of the possible students that could come here and actually didn't, or were never born. So think about every conceivable length that exists. That is an uncountable collection because it is an interval, right? If I have the real number line, so what are some bona fide heights of people? 3 foot 2 inches up to, 10 feet tall. Okay? And I am insisting that for this to genuinely be countable, to genuinely be uncountable, then I would have to have persons of every conceivable height in here. To the most ultra precise, to an infinite amount of precision. So they can't just be 3 foot 2. So I'll have someone that's 3 foot 2, but then I'll have someone that's 3 foot 2 inches plus 0.0000000, as many zeros as you want, and then a 1. And then I'll also have to have someone that's got that same height, but there's one more 0 in there, and then the 1. And so on, forever. And you construct a list of all the possible decimals. So they intend to have you understand that heights and lengths are intervals of the number line. They map directly over to intervals of the number line. So this is continuous. The data can take on any value in an interval. But if you don't modify the statement of the question that way, it really should say countable. But what they're trying to help you understand is that heights
The heights
and
are
lengths,
in interval and-
they form a space
Right.
which is uncountable. Yeah. You could conceive of a female student at some college somewhere that could be any height you choose.
Okay, so we just need to focus on the variable part, which would be like the height or the color or whatever.
Yeah.
So we don't really, okay. Because when you were pointing out the whole college thing, that confused me. And then when you went over to say, like, if it was heights or lengths, then it would be continuous, then I understood why it was continuous.
Yeah. So the key words of this is this part.
Okay,
All the rest of it's garbage.
okay, that's what I was.
And that extra garbage is what's causing the problem. Because if this is my variable, this is a finite collection. So this is not really what they mean. So I'll give you an example. They had a question one time that I got them to change. They just deleted the question. It was the number of red barns in a city. And they put the answer that it was continuous. That's what they had selected as true. I wrote them a letter and explained why that was false. That I couldn't even modify the question to make it be correct. Because even if every building in the city was a red barn, and the city had filled up the entire earth, I could still count them all. There'd be no way to have it be an uncountably infinite collection. I gave them a stronger argument, but that one's sufficient. And they got rid of it. So, but it's like nearly all the questions are like that on here.
So you were saying if the variable, red barns or height, is a number, it should be continuous. Like I have one that's velocities
Okay,
relative to the earth.
okay.
So based on what we just did with the heights, I would think that's continuous with any value in an interval.
Yes. If the airplane is flying and they adjust the throttle, the airplane has to smoothly transition from one speed to the next speed.
But it goes through all of them.
It goes through every possibility. It doesn't jump suddenly from this speed to that speed.
Now, if that question about meteors, velocity, and relative to the earth, if they had defined a time between, a time period, would that have then changed it to discrete?
You would have to, so if I drop a ball, right,
Because between any point in time, they would still have to go between those different,
it would have to smoothly change
yeah.
over time.
Got it. Okay.
Yeah. Okay. Here I just clicked similar question. The areas in square inches of different pieces of paper. This question's okay. It could be better. They could change the word different to any possible. The area of any possible piece of paper. Can you count up? So suppose for a minute that whatever piece of paper, suppose for a minute that I could construct a piece of paper of any arbitrary area you would like. Then would all those pieces of paper be a countable collection? No. It would be uncountable. Because areas is just the two-dimensional version of a length. And lengths were uncountable. Areas are also uncountable. They're just as uncountable. Uncountability means continuous, so it takes on any number in an interval. This problem just hasn't caught up with the times yet. Because it is a mind-blowing fact that so let me go back to the other one. I said here, construct a piece of paper that is any area you would like. Okay? Countable. Uncountable. Because there's an uncountable number of different possible areas. I look at my number line, and I can form an uncountable number of squares, not even getting to the rectangles yet. However, there is a piece of paper so small I mean, if I got down to just one atom of, one cell of this cellulose, that'd be the tiniest piece of paper I could make. And similarly, in space, in the universe, there is a smallest length beyond which anything smaller is meaningless. It's called the Planck length. That interval is so mind-bendingly small. I mean, it's billions of times smaller than a proton. But it is equal to the length such that if I had two light rays, which are waves, and they encountered each other at the Planck length and tried to fit a full cycle or a full period, you know what a wave is, right? Mm-hmm. So if with the highest possible energy light wave that you could ever have, if you tried to fit two of the waves inside the Planck length, it would be an energy so high that it would collapse into a black hole. It doesn't mean anything anymore. You can't even see it. You wouldn't be able to see it anymore. It's inconceivably small, but it's not infinitely small. You can look it up later if you're interested. From that Planck length, you can derive a Planck time. There is a smallest unit of time. It's still not hotly debated, but there are some holdouts in the physics world that don't want to accept it, even though it's been proven experimentally true, that there is a smallest unit of time. There is a smallest unit of space. Space is pixelated. Time actually does not move smoothly from one point to the next. It jumps from one point to the next, like frames in a movie. And we should ignore that here. In the homework, time is thought to be the quintessential smoothly transforming object. It's not actually smooth in reality, but we would ignore that here. Then, if you suppose that you could have any possible interval of time you would like, then time can be thought of as continuous. And that would mean that if I'm talking about different surgical procedures, it's not like the surgeon goes in and says, okay, we're taking out an appendix, start the timer because this takes 3 hours every time. It's going to be different every time. The next patient might take an iota longer, and then all the other patients that they could ever have could form any different possible time that you could conceive of. Time, lengths, they're supposed to be continuous. Lengths really are continuous, but there's a smallest meaningful length in our universe. And lengths are only continuous because they're a direct interpretation of the real number line. The real number line is the only object that you've ever heard of that is genuinely uncountable. Everything else is countable. There's a countable number of atoms that the Earth is made of, right? There's a countable number of molecules of water in all the oceans. Different amounts of time that surgical procedures take at the hospital, they mean for it to be continuous. With the thinking that just map times directly onto the number line and say that all these different possible numbers are different possible times. The numbers of personal cars owned by different households. This question is just fine.
Discrete,
Discrete.
specific,
It's discrete. It can only take on specific values.
yeah.
Because no matter whose household I go to, it doesn't matter how many households I have. Even if I had an uncountable number of households, which you can't have. But even if I did, I'm going to go to somebody's house and be able to count the number of cars that they have. And that's what they're asking for, the number of personal cars. They're going to have 1 or 2 or 3 or 0 or whatever. But it'll never be like you have pi many cars. Yeah. So this will be discrete. It can only take on specific values. Okay. So that's discrete and continuous. Terrific. Now we can move on. The next topic is, so discrete and continuous was talking about variables. And you can define your variable to be whichever. Once you've defined a variable, you can also discuss the manner in which your points are measured.
Thank you.
The manner in which your points are measured is called the level of measurement, and there are 4. And I write it upside down like this because there's like a hierarchy. You can be shown any variable, and the process to determine which level of measurement it is would start with checking, is it this one, or is it stronger than this one and got moved up to here, or is it stronger than this one and got moved up to one of these? Okay. So the lowest order, the lowest level is the nominal level, where it's just a name of something. Like you go to the hardware store and they got the paint aisle with all the chips, and they all got names. You know, there's probably 200 of them up there. Just randomly grab 5 of them. That's your sample, and each of their names is your data points in that sample. And given those 5 names of those colors, you know, sea foam, and what's another stupid paint name? Whatever. You can't do anything with those names like put them in order from least to greatest. You can't look at those and say, oh, well, I'm looking at these 5 paint chips, and that one's the first one. You can't do any of that. It's just a name. Other things that might be at the nominal level of measurement. In the homework, so here's another issue with the homework. Colors are at the nominal level of measurement. But it would be easy to argue that even though those paint chips with those names couldn't be sorted in order. The names themselves don't have an ordering. The rainbow has the same order every time, because color of light is determined uniquely by its frequency. And you can easily put all those frequencies in order. That's why the rainbow comes out in that same order every time. We just ignore that and think about something like dump out a box of crayons and then use the names of those crayons to put them in order from least to greatest. Well, that doesn't really make sense, right? So you would say that a box of crayons, the colors of a box of crayons is at the nominal level of measurement. That name written on the paper wrapping is just that, a name. It doesn't have any numerical content. Another great example would be your phone number. That's not the greatest one. Another great one would be your license plate or your social security number or your driver's license number.
So it's something that you can't necessarily put in any type of order, it's just what it is.
It's just what it is.
Okay.
Like driver's license numbers, if you were the governor of the state, they will let you pick your own driver's license number up to some certain, like, for example, when George W. Bush was governor of Texas, his driver's license number was 3. That doesn't mean he was the 3rd driver that they ever licensed, right? That 3 is meaningless. It's just a name. It's a direct mapping over to him, to his name. So that 3 for a driver's license number stood in place of his name. Above the nominal level of measurement is ordinal. If you're looking at a variable and you're wondering if it can graduate up to ordinal, then it would have to be the case that you could, that there is a well-known ordering. If you went to the Olympics and ran the race, and you came in first, and they gave you the silver medal, you'd be upset. Because you know that those have an ordering. And they go gold, silver, bronze. And everyone knows that. Right? These also have no numerical content. But we know that that one is greater than that one, and that one is greater than that one. They go in order. It's possible to have things that are at the ordinal level of measurement that are just numbers. The integers are at the ordinal level, and they go 1, 2, 3, 4, 5. You know which one is greater than which one. What's another well-known set that has a well-known ordering, and you've known this set since you were 4 or 5 years old?
The alphabet?
The alphabet.
Yes. It's the first thing I got today.
The alphabet, alphabetical ordering, you know? The alphabet is ordered. We all know its order. And that's it. But you can have things that are numerical, such as
Would it be like, could date of birth be, like if we were to order by a date? Like Like, is dates ordinal?
Yeah.
Okay.
Only because we have a perception of cause and effect, now and later, before and after. Without that, they would not be ordered. The next two above this have to be described simultaneously. The third one is called interval, and the final one is called ratio. I don't completely understand their names for these, but I can just go with it. For both of these, interval and ratio, they have the same feature with just one distinction between the two. So for both of them, they satisfy the property, and we can just sum it up in 3 words. That differences are meaningful. Differences are meaningful. So that means that well, now I have to correct something about your example with the dates. So dates is at least ordinal. It's better than nominal, okay? Because we know how to put them in order. Can it be any better than one of these? All right. So the date that you're going to graduate, take today's date and subtract it away from the date that you're going to graduate. Then we'll have a difference, right? Mm-hmm. And that difference that you're going to get will exactly describe the number of days you have left in school. It's meaningful. But if I had went and got two Social Security numbers, even if I said put them in a stupid order, like just sort them in numerical order and just pretend that it's at least ordinal, then the difference between two Social Security numbers would not necessarily also be another Social Security number. If I took, here's a better example. If I took a list of college rankings, right? Harvard is usually at the top, and then Stanford or whatever. And I took the 5th school on the list minus the 1st school on the list. It does not produce for me a new college that has a ranking of 4. You know what I mean? So differences wouldn't be meaningful in that ranked list of colleges. So it would have to stay down here at ordinal.
Would that ranked list of colleges be ordinal or nominal? Because
if Harvard got ranked first but appeared 30th on the list, they'd be upset. We know what the order should be. It should go 1, 2, 3.
Okay, but then let's apply that to like college football. Would that just be nominal because it's variable? It changes every year, or because Alabama always thinks they're one, they should be first, even though they didn't even finish in the top 6 this year.
Roll Tide.
Oh, interesting.
No, I'm kidding. I'm kidding.
Go Frogs.
Look, you have facts, and then you have like their goofy opinion.
Well, wouldn't Harvard's ranking be an opinion? Because if you potentially, it could be the most, I don't know, intellectual or top school for that, but not for art.
Gotcha.
It's classified, right? Whatever.
So what we're saying here is that just suppose that we had a ranking. Not that you agreed with it, but that it was just there. Like maybe instead of ranking, I just pick up a list of colleges. And they're just in some random order, but they're all numbered, 1, 2, 3, 4, 5. Then the fifth one minus the first one won't mean anything because it doesn't yield for me another college on that
Okay,
list.
so like a student ranking would be ordinal, not nominal, but it would not, it has no difference, meaning so it stops at ordinal.
Yeah,
Okay, I understand.
okay. Yeah, a student ranking is probably a better example because everyone would strongly agree with like, whatever your GPA is, that produces your rank. And the difference between two students is not another student on the list.
Got it,
Okay.
that makes sense, thank you.
So for both of these, differences are meaningful, but the difference between them is that interval has no starting point. And ratio starts at 0. The one on this list of 4 here that is the hardest to think of an example, number 3. If you came up with this example and didn't see it somewhere, I'd be impressed. And then I'd be even more impressed if you came up with a second one. Ratio, that's kind of easy. The amount of time that I wait in the Starbucks drive-thru, that's something at the ratio level of measurement. Because if I took two different, Joe, I got Alice and Bob, and they each waited however many minutes in line. Well, then when I take the difference of those two, I get another number that describes for me how much longer one waited than the other. It started at 0. You can't wait in line for any less than 0 minutes. So you would also agree that you can't have an age lower than 0. Your age is a good example. That's just a subcategory of time. What about that example for interval? We should play hangman with it. You know what I mean?
Let's do it.
It's got 11 letters. Starts with a T.
And one word.
This is 11 letters, it starts with a T.
Mm-hmm.
I feel like I know 11-letter word.
Okay, so I just put, no, never mind, that's not right, because it doesn't have a temperature.
Nice.
There you go.
Temperatures have no starting point. So look at the Celsius temperature scale. If something has the temperature of 0 degrees, it's not absent of all heat, right? It can get colder. So on that scale, 0 is definitely not a starting point. And then you've got Fahrenheit scale, right? Same deal. 0 degrees Fahrenheit, it can get colder. 0 degrees Fahrenheit is really cold. That's colder than 0 degrees Celsius. And then there's that other scale, okay? And there's that well-known quantity, absolute zero. However, it is not possible to have anything become that temperature. Right? So that scale, the Kelvin scale, has a lowest number. I could keep going lower, then I could say -1 Kelvin, but that really isn't going to make sense because 0 Kelvin is the temperature for which nothing could ever achieve. At that temperature, there's no more kinetic energy in the molecule. Heat is the kinetic energy of the molecules. That's when you feel heat, that's what you're experiencing. And you would have to have no more motion at all. And quantum physics doesn't allow that. There's always a residual motion. Even if I had a single electron, it still has a spin, and it will never stop. Even with as the universe expands into in a googol of years, that's a 1 with a million zeros after it. After that many years, when everything is inconceivably far apart, and your observable universe shrinks down to consist in nothing but a single proton, then even that will get ripped apart into nothing, and everything will finally cool off to the same temperature. It still will not be 0 degrees Kelvin. You just cannot achieve it. So, not even that scale has a starting point, because if it got colder, then it could still get colder again, and it would just keep asymptotically approaching that 0 degrees Kelvin, but never really reach it. So temperature is at the interval level of measurement. Time is at the ratio level of measurement. Then your favorite films. Well, this one's deceiving.
Yeah.
Because I don't know if they mean, I can interpret it two ways. I have a cardboard box and I've tossed into it all my favorite films, and I say, over there's all my favorite films. But do you have, can you dump out the box and then put them in order? Right? Did they say that? I think that that's what they mean here.
So it'd be ordinal.
I think it would be at least ordinal, right? Because if it was just a box and it had no order, then it would just be nominal. But if I ranked all of my favorite films, then it would be at least ordinal. Can it graduate up to interval or ratio? No, because even though it would seem that there's a starting point, right? The differences aren't meaningful. If I take the first film minus the third film, it does not give me another film in the box that's got that ranking. So then they specifically mean the other interpretation, that you didn't put them in order. That all that you did was make a box and said, yeah, all those are my favorites, in no specific order.
That is poorly written.
Yeah. The only way that they could have made it any clearer, though, is to say your favorite films in no specific order, and that probably would have given it away.
Even like list of favorite films, I think would have
An unordered list?
applied in a list, don't you?
How about you write the name of all your favorite films and put them in a hat? I mean,
Yeah.
well, then that's just right back to the box full of them.
So, if would a to-do list then just be nominal?
So long as you could do any one of them, you could do them in whatever order you'd like.
Not instructions, just a to-do list, like, yeah.
Yeah. Like you use the little dots instead of 1, 2, 3. Acres of land. If I have 2 acres of land, does that number 2 also describe the quantity of acres? So it's above nominal. If you have 3 acres of land and I have 2 acres of land, then you have more, because 3 is greater than 2. So it's above ordinal. Then is it interval or ratio? How come?
Because there's a 0.
Yeah,
You can have none.
that's the least amount of land you could have. That's the smallest number of acres that you could do, ratio. And if you guys, so you guys should be doing these with me, and if you have a question on yours, then we'll do it. Monthly temperatures.
Would that be ordinal because they gave us the specific ones to work with?
It's at least ordinal.
Okay.
And it can be bumped up to ratio because there's history.
Temperature is the classic example of something that didn't go up to ratio. So if,
But because they gave us one that starts 60,
uh-huh,
wouldn't that then make it ratio since you do have a starting point? Since they gave us
0 has to be a starting point.
0 has to be the starting point.
0 is the starting point, yeah.
Got it, so then that would be.
Because,
equal.
well, so, this is another one of those questions I'm not sure about. It's poorly written. Did they mean this? Did they mean to say, come on with it. Did they mean to say possible monthly temperatures? Because if that's what they meant,
Interval.
interval. But they didn't say that. They gave us a finite list, and it might as well say, these numbers.
Yeah.
That's the other interpretation, is that you've got a box and it's got these 5 numbers. Well, it's at least ordinal. But if I have restricted myself down to only having 5 different temperatures, then I can take differences of these and be able to, know how much hotter one is than the other, but I can't get down to 0 or anything negative. I don't think it would even be interval or ratio. So let's first assume that they just meant that it's just these numbers and you can only order them. And if they don't like that, then maybe they meant interval. And if they meant interval, they should have said that it was just possible monthly temperatures. So then they would have to come over here and say that you had all of these temperatures and all of, a whole bunch of other temperatures that the thermometer could have ever said. Okay, that's what they really meant in this case, was that you had these 5 temperatures, and then you also had All the other temperatures and that's what it would take to be at the interval of, you literally need all the temperatures.
Okay, mine was in inches.
There they mean
Monthly rainfalls.
monthly rainfall in inches.
Yeah, and it gave different.
And it gave a discrete list of them.
Uh-huh.
Then, yeah, in the same fallacy, they give you a discrete list. You might think, well, I can only order this list. But they really mean, really they're asking you about lengths. Are lengths, did they graduate all the way up to the top to ratio? You can't have a negative length. That doesn't make any sense.
Has to start with zero.
Has to start at 0. All right. There's got to be one of those we didn't cover,
There it is.
the monthly rainfall.
Ratio.
Maybe I'll have to write them again about this question 5, because it looks like the style of question 5 is always going to be they ask you something and then produce a list, a finite list. Well, that's not what they mean. They can just delete all this other stuff over here. And then it's exactly what they meant. They mean to ask you about ages of children.
That's ratio.
Ratio. But if somebody were to interpret this as, my 5 kids are aged 4, 5, 6, 7, and 8, you can only order them.
But I had that one.
Yeah, it's ratio.
I put order line first, and then I went back and I put ratio.
Yeah. Okay. Let's take a quick break. And then when we come back, we're going to do sampling techniques. And then that will be it for the words. We can go on to the next thing. And it doesn't take that long. It's actually not too bad. So discrete and continuous were a discussion about features of the variable. And then levels of measurement was about how you measured the data points for that variable. And then sampling techniques is about how do I collect those data points in the first place. And there are 5 of them. There are 5 of them that we're going to talk about. There are other ones that are more sophisticated or some mixture of these. And unlike the levels of measurement, there's not like a lowest order sampling technique, right? Where it's like this is the junkiest one or something. However, there is an order that I would like for you to approach the question with. And that will be the order that I define them, kind of like a flow chart. So there's these 5 different sampling techniques. And the very easiest one to recognize is called the systematic. Not systemic, systematic. The systematic sampling technique. It would be a great choice if you had like a list of phone numbers, or if you had a list of registered voters, or if you were at a factory and you needed to collect a sample of the things that they're manufacturing. It goes like this. You would you pick 2 positive integers randomly. Pick 2 positive integers. Like maybe my 2 positive integers will be 6 and 3. Then I can determine the position on the list of all of the registered voters that I want to be in my sample. The first one in my sample would be voter number 6. And the second one in my sample would be voter number 9. And the third one in my sample would be voter number 12 on the list. And you just keep going until you have however many you want to be in your sample. So the equation looks like this. That's your first random number that you picked, and then this one This green one just increments by 1 every time, and it multiplies against the 3. It has the effect that you're just starting at 6 and adding 3 every time to get to the next one. So it's 6, 9, 12, 15, 18, 21, and so on. And if I go all the way out to n, then this would be the n plus 1 element member of my sample, because this was the first one, and this was the second one, and this was the third one, and so on. Because that started at 0. That started at 0. This was the first one, and this was the second one, and this was the third one. So evidently, whichever one I'm at is always just one more than that number. And if I go all the way out to n, then I have this many in my sample. So if I wanted like 20 to be in my sample, then the very last one would say 6 plus 19 times 3. So the 20th one is 6 plus 19 times 3. That's 63. And obviously, if you've only got, like, let's say, 100 things on the list, then you've got to pick these two numbers such that you don't go past the end of the list. You can't be coming up here and picking like, 1,048,000 and then 630,000, right? You're not gonna have a population that big. That's systematic sampling. Very easy to recognize. So if I'm looking at a question and they want to know, what is the sampling technique here? The first one I'll check is it systematic? Yes, no. If it's yes, I'm done. If it's no, I move on to so is systematic? If it's yes, we're done. If it's no, then you have to ask yourself, is it partitioned? If it is, whatever that means, if the answer is yes, then it will be one of these following two sampling techniques, because only these two that I'm about to tell you involve some kind of partition. Where a partition would be something like a map is a great one. You have the United States and all the state boundaries partition the United States into 50 different pieces. You know what I mean? And every square inch of the United States is in exactly one of those partitions. There's no spot where this piece of land is in Texas and it's in Oklahoma. It's in one or the other. Know what I mean? Okay. You either live inside the city limits of Garland or you live outside the city limits of Garland. That's a partition. So if it's partitioned and the answer is yes, then it's either stratified it's either stratified or it's cluster. If the answer was no, then that'll be what's on the next page. And if you get no, if there's no partition involved, and you get to that next page, then there's just the two options left, and they are so different from one another that it becomes easy to see which one it must be. But stratified and cluster can be confused easily, because they'll use a bunch of the same words, but just in a different order. And those words are random and every. If I do random and then every, it's one of these. But if I do every and then random, it's the other one. So here's what we'll write. It's stratified if I look at every partition go to every partition and make a random selection. It's cluster if I select a random partition and then collect for my sample every member. So here is my fantastic example. And I'm so proud of myself because I thought of this example before COVID even was a thing. You are working at DFW Airport, and there is a worldwide contagion. And your job is to check inbound passengers, see if they're sick. Well, if you wanted to do a stratified sample, then you would go to every single airplane, because the airplanes would naturally partition the passengers that are incoming. You would go to every inbound airplane and randomly select some passengers off that airplane. And then do whatever you're going to do, check their temperature or something. That would be a stratified sample. You went to every airplane, you randomly selected. But if you wanted to do a cluster sample, then you wouldn't go to every airplane. You would randomly select some number of airplanes. You could randomly select, however many you want, 2 an hour, or whatever, at least one. You randomly select some airplanes, and you check every passenger on the plane. That's a cluster sample. You see the difference? Okay. If there is no partition, so that was what you do if there is a partition. If there's no partition, then you must choose between it's either random. Sometimes this is quantified with the word simple. It's a simple random selection. Or it is a convenience sample. Okay. And these are wildly different. The random sample would only qualify as random if it is truly random. Something like, I've got this list of people. How am I going to pick which ones to go? I have like a bingo ball machine here, or the lotto, the stupid lottery machine that they have, right? And all the balls are flying around. And it's a totally random event which ball is going to come out of that machine. It's got a number on it, and whatever number that is, that's going to be your sample. There has to be some kind of mechanism ensuring that it is actually random, like a bingo ball machine. Or you could even say drawing names out of a hat, or drawing numbers out of a hat, or you could use a random number generator from a computer. Secretly, that's pseudo-random. But there's got to be something involved making it be random. And if there's nothing there making it be random, it's convenience. So let me ask you, if there's somebody in the mall, if anyone still goes to malls anymore, and they're standing there, they've got a clipboard, and they're trying to get people, they've got like a one-question survey, do you like our product, or whatever. And there's all these people walking through the mall, and the surveyor is just, they're looking like, which one of these suckers can I get to answer my question? And they come and ask you, and you just blow them off. You say, no, I gotta go. Well, then they come and ask you next, and you go ahead and answer their dumb question. But they didn't like the cut of your jib, and so they skipped you. Is that random or convenience? You were selected to be in the sample, and you didn't participate. If you had participated, it would be something different from convenience. You were not selected for whatever reason. Two of you were selected to be in the sample, and you both participated. There's other sampling techniques out there where you have some kind of strategy to pick, to take your population and pare it down to people that we need to be in our sample. And if anyone doesn't respond, it would have to immediately devolve to a convenient sample. Have you ever seen those surveys they send out in the mail and it comes with $1, like a real dollar? You know what I'm talking about? That's so that they can justify that they did not do a convenient sample. Back in the day, I forget which presidential election it was. Oh yeah, I know. It was, there's a famous picture out there of a guy holding up a newspaper, and the headline says this. Have you ever seen that picture? Huh?
I was born in
40s?
2001.
50s? Yeah.
Early 1900s, a long time ago. It was the presidential election between these two people, Harry Truman and the newspaper was so confident that this guy had won that they went ahead and printed the paper. What happened? There was a very famous magazine that millions of people subscribed to in America. I can't remember what it was called. It was some magazine. And every election, for however many elections before that the magazine had been around, they would send out surveys to all of their subscribers and get their temperature on the presidential election to see if they could make a prediction about who would win. And they were right for a lot of years, and people began to trust their surveys. But then a man named George Gallup came along. You've heard of the Gallup poll, right? This has become a brand name of excellent polling techniques. And the people at the magazine, whatever it was called, I forget, they had a huge sample. It consisted in everybody that returned a survey. I think that what they did that year was they did surveys by telephone. They just called all their subscribers. Right? They called. But George Gallup was a really smart mathematician, and if their sample was, 200,000, I'm not sure that that's the number, but if their sample was 200,000, then his was something like 5,000 Americans or less. You know what Ancestry.com is, right? You ever used it? You have? Like me too. I built my family tree just as far back as it would go. And this guy's on it. He's the only famous person on it. But I thought it was peculiar that he was on there. Yeah. And naturally, you can guess what happened. They were wrong. He was right. Why did he come out right? Because he created a list of these 5,000 people and insisted that every one of them, he had some kind of strategy for picking this people. And he selected them in such a way that this sample was demographically identical to the American population. And this sample was not. This sample consisted in people that had telephones. And at that time, that was a big luxury. And a lot of Americans didn't have telephones. And they didn't like Dewey. And they didn't vote for him. And he didn't win. Truman won. And and George Gallup predicted that. And then he went on to predict, I forget how many in a row, correct. So, your convenience sample, it will become a convenience sample just as soon as you, if someone has been selected to be in the sample and you don't get their information, it is a convenience sample. If I go to the airplane and I have to check every person in the airplane, and for whatever reason, this one person locks themselves in the bathroom for eternity, then I had a convenience sample, really, and it wasn't a cluster sample anymore. A researcher selects every 863rd, not thirth, Social Security number and surveys the corresponding person. So you go in their flow chart. What's the first thing to check? Is it? Then you're done. Can't be any of the other ones. A man is selected by a marketing company to participate in a paid focus group. The company says that the man was selected because everyone in 6 randomly selected towns was selected.
It's a cluster.
It's a cluster. We partitioned the population by the towns. There's more than 6 towns. There's however many towns there are. They randomly selected 6 of them and interviewed everyone in the town. Cluster. A large company wants to administer a satisfaction survey to its customers, to its current customers. That might be important. Because if you're a previous customer, you might be unsatisfied, right? Using their customer database, the company randomly selects 90 customers and asks them about their satisfaction. That's just random. I mean, they told us it was a random selection. But we know it's not something like stratified. Even though stratified uses a bit of randomness in there, there's no partition.
So the database list of customers is not partition. Like, that's not considered a partition.
How would it be, where would the partition be? I'm looking at the database, how is it divvied up?
Current versus not. Versus potential. Like, is partition physical partition, like you talked about with like the map?
It can be a virtual partition where I imagine a boundary between these two things, yeah. If I went out to the border between California and Nevada, there's not a fence, you know. So.
But it wouldn't be either one of those, because it wouldn't be stratified or clustered, because it wasn't if it was partition, if current customers is considered a partition, they didn't randomly select one of them, and then they didn't interview all members of the one they selected. So it's neither of those, because it's not random and every, or
Yeah.
every and random.
You know it's not cluster because they didn't interview everybody
Right.
in one of the segments, right? In one of the partitions. So then we're having to choose, is it stratified or did it go down to random? Well, this word current is a trip up, because they only want to administer the survey to current customers.
Right.
If they didn't use that word, you probably would never ask if there was a partition. But this word somehow might imply that if I went over to their database, it could still have non-current customers. Whatever current means. They didn't buy anything from us in 5 years. They're not current. So, I believe that what they meant is to either not use the word current or that their database only consists in current customers. If the database was partitioned into previous customers, current customers, it would be a stratified sample. But that would be a dumb stratification because, or, you know,
Well, it wouldn't, if it was staying like that, because they did current, stratified is excluded because it's not every partition.
actually, yeah, you're right.
So it wouldn't be part of that, yeah.
Yeah.
Okay. So it still follows that flow chart of
So I guess here's what I meant. If your partition is the trivial partition that has only one warehouse, then stratified and random are the same thing. Because there's just the one partition to go to.
Got it.
There's not a second
Thank
one.
you.
Yeah. It would be dumb to go ask my previous customers about their satisfaction level.
Their reason they're previous.
Yeah, they either hate us, or, you know, they're dead, or they ran out of money, or whatever. You know, they're not buying from us anymore. They have either no opinion or they don't like us. Can't be good. Oh, you guys are great. I get the greatest service from you, but you haven't bought anything in 10 years. So, Carrie divides up her day into 3 parts.
Partition.
There's a partition. She then measures her mood at 4 randomly selected times during each part of the day.
Stratified.
Stratified. A woman experienced a tax audit. The tax department claimed that the woman was audited because she was randomly selected from all the taxpayers.
Is that just a random?
Sure does read that way, yeah. Because the only people can get tax audits are the taxpayers. She was randomly selected from all the taxpayers. We're going to do a similar version of this question. Same thing.
I got that one, man instead of woman. Same question.
Mine said, and it might be the next one, it was,
Was it from people in certain tax brackets?
no, it was, people, it was in random towns, but they were auditing everyone in the random towns.
You already know. There is another version of this question that I've seen before, which is like the woman was selected randomly from the taxpayers in her tax bracket.
So that would, the tax bracket would be a partition,
Mm-hmm.
okay,
And she was randomly selected, so
stratified.
stratified. Here we have a partition. They've used the word partition, there's no question. Unemployed, employed, full-time, employed, part-time. Surveying 44 people from each category. I guess we are left to,
Assume they randomly selected those 44?
yeah, that they randomly selected the 44 from each category, and that there's more than 44 in each category. Or else it would become, well, it would become a census if you interview every person. So,
Stratified.
yeah. Because she went to every category. Time for, okay, all that's done. All the word part's done.
Time for me.
Actually, I got one more word for you. Oh, man, 2 more. It's okay. Frequency table, histogram. You have the frequency table, you have the histogram. Histogram's like a chart. It's like a bar chart. You might, in fact, precisely get it mixed up with a bar chart. But a bar chart is technically different, though. A frequency table is just a way to take my data and organize it. It's an organization of the data. If I had a sock drawer and it's got white socks and black socks, and it's got 120, wow, that's a lot of socks, and then it's got 80 black socks, then this is a frequency table. The classifications of socks are the two colors, and the frequency of my observations are in the other column. And that's it. That's a frequency table. Okay. Now, color of socks is at the nominal level of measurement. So you can also have a frequency table that has classes that are not at the nominal level of measurement. And if that happens, that's where it gets really interesting. Because what if we had back to the how long I waited in the Starbucks line. You could wait between 0 and 0 minutes and 59 seconds. Or you could wait from 1 minute to 1 minute and 59 seconds. Or from 2 minutes up to 2 minutes and 59 seconds. And let's assume for a minute that the way you're measuring that time is just with a regular old watch, and the most precise that you can get is just to the second, right? Okay. You don't have like some atomic clock measuring how long it took to get your coffee. Then these are also classes and I can also measure the frequency of my observations. I'm standing at the drive-thru and I'm watching everybody come through for the morning. I'm taking a census, let's say, for that day. And I saw only 2 lucky people, or for an hour. I saw 2 people get through in under a minute, but 8 of them were in the next class, and I saw 10 in the third class, and then 6 in the other class. And then that was it. That was all that I saw for that period of time. Well, you can easily answer the question of how big was that sample. You just add up all these frequencies, right? I'd have 26 people in that sample here. I just added up all the frequencies. No problem. What you lose here is this organization. This is an organization of my data, but you don't know anymore that for these 2 people here, you don't know anymore exactly how long they waited, right? All you know is that it was somewhere in here. So it's like a kind of a demotion from the. No longer is it the raw data. You don't have the data set. I can't recover the data set from this frequency table. Now, histogram is a picture of a frequency table. They have a one-to-one correspondence with each other. If you have a histogram, then you can easily write down the frequency table. If you have a frequency table, you can easily draw a picture of the histogram. So I'll draw bless you. I'll draw a picture of this histogram. So this line at the bottom is the number line. And there's 1, there's 2, there's 3, there's 4. Notice that these classes partition the interval from 0 to 3 minutes 59 seconds. Everybody is going to belong to exactly one of these classes. They won't belong to 2 of them. That's why I have to end it with the 59 seconds. I can't say it ends at 1 minute, because then if you waited in line for 1 minute, did you belong to this class or that class? So that's why they're split up like that. And the first bar would have a height of 2, and the next one would have a height of 8. And the third one would have a height of 10, and then the last one has a height of 6. And if I just indicate how tall those bars are, with like a little number above it, then you have the exact same information as the frequency table in the picture. Now we're going to use this fact that you can go back and forth to turn the rest of the problems into a cakewalk. It will be so easy. And for the poor students that don't know about this, they will struggle with these last few problems. Because here they've given us the commute times of 45 different commuters. And my job here is to fill in all these numbers without making any mistakes, right? So the first thing I would need to do is to fill in all the classifications. Well, they've told me to use a class width of 15 minutes. Back here on my example, what do you think the class width is?
59 seconds.
0 to 59.
It's actually 1 minute. The class width is not this width. The class width is the difference in consecutive lower limits. So, the difference in consecutive lower limits. Like for example, maybe you could see it this way. This one starts at 1 minute and 0 seconds. And it ends at 1 minute and 59 seconds. So there is 60 seconds there. That's a minute. This gap between 59 seconds and a minute is a consequence of the precision of my measurement. Yeah. Yeah. So when I go to make this, all these classifications, I'll start off by just going straight down the list and adding 15. The next lower limit is 15, the next one after that is 30, the next one after that 45, and then 60, and then 75. And just out of curiosity, what would be the next one after that? It would be, what, 90? Okay, keep that 90 in mind. Now I'll fill out all of the upper classes. Okay, we already said that would be 14. And you know that it's 14 because it's just one less than this one. Okay? Now, that one right there is just gonna be 29, because that's one less than 30. It's also true that 14 plus 15 is, or excuse me, yeah, 14 plus the class width is 29. You can just add the class width the whole way down over here also. But it's going to be a little bit easier to just look at that number 45 and say that this one should be 44. And I'll look at the 60 and say this one should be 59. And I'll look at the 75 and say this one should be 74. And I'll look at that 90 that's not there and say that this one should be 89. And now I've got all the class limits. These are called class limits, the lower limit and the upper limit. Then comes the hard part, the frequency. There's a bunch of data points to be looking at. There's 45 of them. It would be, I could do it. I could put all these, I'd make me a table or something, get organized, sit down with no distractions. I could figure out how many were in each class. But that sucks. You can just click this two blue boxes here and say open in StatCrunch. StatCrunch is a piece of statistical software, comes free with the MyLab. And when you click open in StatCrunch, it grabs that data set and just puts it in the first column. Okay? So there, I've got my 45 numbers loaded up. We have the raw data. If you have the raw data, the data set, then StatCrunch can make for you the histogram. And with that histogram, I can just, in a snap, see how tall each bar is and know what the frequencies are. I'll go to graph, histogram. I tell it where the data is located. VAR stands for variable. It's located in that column. I need to tell it where to start and what the width is. Well, here we started at what, 15? Or no, we started at 0, and the width was 15. The only other thing to do is to select the box that says value above bar. And then you click compute. And it made me the histogram.
So there's 4 people that going up first.
Yeah.
Column with the frequency too.
So this first class has a frequency of 4, and the next class has 15, and the next class has 12, and then 8, and then 5, and finally one poor soul taking more than 75 minutes to get to work. Which is us if we have to come to work in the rain during rush hour from virtually anywhere around here, unless you live right down the street. And that's it. Check answer. Good job. They ask a few more questions after that. They ask this question about what it means to be a normal distribution. It's a little early for them to be asking about normality, but you can determine the shape of a distribution the shape of a distribution is, if I have a histogram, no matter what that histogram is.
Really quick question.
Yeah.
I don't think I put this in right. Because I have the same questions you for the frequency was 4, 15, 12, 8, 5, and 1, right? The last one was 1.
I doubt that you have the
My
exact
numbers were
same.
different. I did the graph with him, but I had 5 in the first frequency, not 4. like he did.
I 12, 13.
45 commuters,
It's like on my
16
phone.
The data set was probably different.
It was,
Yeah.
that's what happened, okay, I need to do that.
Did I use that word right? Data set?
Yeah.
Yes. What was the chart thing called?
Yeah.
Exit out of it.
You go to graph, histogram. So you have to open your data in StatCrunch.
Yeah.
Okay,
Yeah.
StatCrunch, okay. Okay, that's,
It opens up your 45 different commute times. Yeah, okay.
Mine's still saying that I entered something.
On the frequency table,
Yeah, when I went to go
it's still saying it? Okay, let's just make sure we're doing this right again. So
start.
I click here to look at my data. I click this box to open it in StatCrunch. The StatCrunch window opens and it all by itself puts in this list. I go to graph, histogram. 3 things to do. You tell it where the data is located. It won't even let you proceed unless you tell it that.
okay.
The mistake is more than likely here at the bins. It starts at 0 and goes to 15.
That's what it is, okay.
And then you select value above bar and compute.
You said value above bar.
Yeah.
Oh, I see it now. I can see it. Okay. Gotcha. Thank you.
Mm-hmm.
I have a different graph, but I put all the numbers.
Are you sure that you've done the limits correctly?
0 to 14, 15 to 20.
Is the class width in yours exactly 15? Does it say it in the problem?
Is the class for 15 minutes a weekend? Or go to class limit of 0 minutes?
That's not 90. 75 plus 15 is 90. So 90 is this imaginary class underneath here.
It's okay.
That number down here is 90. So that would be
Okay.
one less than 90.
Okay,
It's 89. That's the problem.
thank you.
Do the data appear to have a normal distribution? What is the shape of a distribution? Well, here's my histogram, some random histogram. You can get a sense of what the shape of the distribution is by drawing. This is not a rigorous definition. You draw a smooth curve through the tops of the middles of each bar. And whatever that curve is your distribution. And it has a shape. Mine's shaped like a snake. Okay? That's not an official statistical distribution shape. I have a very peculiar histogram here. But there are 3 distributions that we need to know, I guess, right off the bat. The one that's shaped like this, it goes up, it goes back down where it came from, it goes up to a maximum, it comes back down to where it came from, and it's roughly symmetrical. So it needs to go up and then come back down, and it needs to be symmetric. You could also have a skewed right distribution, or you could have a skewed left distribution. Now, we'll have a more rigorous definition of what it means to be skew right or skew left. For now, you just look at which side has the tail. This one's got like a tail, skinny part here. There's the body, this is the tail, it's on the left, so skew left. Here's the body, and there's the tail. Tail's on the right, skew right. And they are asking us in this question if this has a normal distribution. So we would need to be staring at our histogram to see if it has a normal distribution. And it's not symmetric. It peaks at the second bar. Right? There's 6 bars here. If it was going to be normal, then the 2 bars in the middle would be the tallest. Right? In fact, this thing is skewed to the right. So I will say no. It goes up and then comes back down, but it's not symmetric. Examine the data and identify anything appearing to be unique. Select all that apply. So you can open back up your data and stare at it and see that, I mean, there's a lot of them ending in 0. And if you think about it, that would make sense because most people, if I said, how long does it take you to get to work? They're going to say, it takes me 20 minutes or it takes me 30 minutes. And there's going to be just a handful of people that are like, it takes me 36 minutes. It's not the same every time in the first place. And second, those people are probably nerds. And we don't have them in our sample. So it makes sense to us that these may be estimates. And that would be an important consideration if we're trying to reach some conclusion. If we're serious about this statistics stuff and we're trying to reach some important conclusion, it would be worth it to recognize that a bunch of our data was estimates. The unusually large value of 80 minutes, does it appear to be an error? I don't have any reason to believe that that's an error. It could just be that that person they live 80 minutes from work, so that's their thing. Maybe they go to work once a week. Number C, you can't conclude, and D is nonsense. Because knowing how long it takes you to get to work is exactly what it means to be quantitative. It's not categorical. Categorical is just another word for nominal. All right, question 13. We have only a couple minutes left. You have 13, 14, and 15. Let's skip 13. 13 is just like the previous question, except they don't ask you all this extra stuff at the end. You'll open up the data set, make the histogram, fill the thing out, and move on. Question 14 has this new idea of what's called a relative frequency table. You can easily construct a relative frequency table from the frequency table. Here is how. Make another column, call it relative frequency. How do I get the numbers? The numerator is whatever the frequency was, and the denominator is the total. The sum of the relative frequencies must be 1 then, because all of these these numbers added up to 26, and the denominator is 26. 26 over 26 is 1, which is 100%. So, what they give you here is they give you 2 frequency distributions. There is nothing you can do here in StatCrunch. Even though you have the boxes, you don't have the raw data. It can't make for you anything from these summaries. But you don't need them. Look, it's about non-filtered cigarettes and filtered cigarettes. Okay. A cigarette that doesn't have a filter is you're going to get more tar. The filter filters tar. So filtered cigarettes should be lower tar. That's our natural thinking. And that is exactly why in this non-filtered cigarettes list, you don't see any that have in the class with the low tar. Let's go ahead and just put those other classes that aren't there and just and record a frequency of 0. Okay? So the class that was before this one, right? There's the 17 to 21 class. Before it was the 12 to 16 class, and it had a frequency of 0. And before that was the 7 to 11 class with a frequency of 0. Okay? And this adds up to 25. For the filtered cigarettes, the missing classes would be the class from 27 to 31 and 32 to 36 and 37 to 41. And they all have a frequency of 0. And this also adds up to 25. Okay? So my relative frequency table for the filtered cigarettes, for the non-filtered. For the non-filtered cigarettes, the relative frequency would go like this. Well, the first class from 7 to 11 is 0 out of 25, which is 0%. And then the 12 to 16 class is 0 out of 25, which is 0%. They want a percentage. And then the next class from 17 to 21, that's 2 out of 25, which is the same thing as 8 out of 100. That's 8%. 8%. The next one is 2 out of 25 again. So you get 8%. And the next one is 13 out of 25. And that's 52%. And then it's 7 out of 25. That's 28%. And then it's 1 out of 25. That's 4%. So all of these boxes right here, the answers that go there are 0, 0, 8, 8, 52, 28, 4. Okay. Each of these percentages, like that 52%, comes exactly from the fraction 13 over 25. And then I just need to do the same thing over here with the filtered cigarettes and make this column, or the other column. And once you've done that, I think that all they ask you is, do filters appear effective? Well, yes, because
0%.
yeah, all the high tar classes have zeros. All right, it is past 4 o'clock. Then there's just the one question we did not discuss. It is actually super simple. It is the cumulative frequency. If you have to go, take off, but I'll stand here and do this last one right quick. It's really easy. The cumulative frequency just needs to accumulate as you move through the classes. These classes are not partitions anymore. They overlap, right? If you're less than 55 degrees, then you could be in any of the classifications below. You could be in that class, or you could be in this class, or this one, or this one. So all you do is just add the numbers up as you go. The first one is 3, and the next one is going to be 4 plus the previous one. So this is 4 plus the previous one. And the next one's going to be 5 plus the previous one. And the next one's going to be 14 plus the previous one. And then 6 plus the previous one. and 5 plus the previous one, and 1 plus the previous one.
And just the previous one?
The previous one is the sum of all the ones before it.
The previous one on the cumulative, not the previous.
Yeah.
Got it.
All right?
All right, thank you.
See ya. And that is it. When we start next class, we will pick up with this idea of frequency tables and histograms and just elaborate on it some more.